Welcome back, students. In our first session here, we introduced some important families of carbon compounds. Specifically, we talked about alcohols, aldehydes, ketones, and carboxylic acids. So in this next section, we're going to explore each one of these families in a little more detail. We're going to begin with the alcohols. Remember, alcohols are carbon compounds that contain the hydroxyl or OH group. We can classify alcohols based on how many substituents are attached to the carbon that's bearing the hydroxyl group. So we have primary alcohols, which have one substituent, as you can see there on the bottom left. Secondary alcohols are those that have two substituents, as you can see the one in the middle there. And tertiary alcohols have three substituents. And when we say substituents, what we mean is other carbon chains or portions that are connected specifically to the carbon where the hydroxyl group is attached to. In terms of properties, we are familiar with the use of boiling point as an index, as a window into the types of intermolecular forces that are present in substances. So if you compare an alcohol with a hydrocarbon of similar size or similar molecular weight, alcohols are going to have relatively high boiling points, and this is because of their ability to form hydrogen bonds, as you can see here on the left, between the partially negative oxygen atom of one molecule and the partially positive hydrogen of the neighboring molecule. Don't forget, the hydrogens that are attached to carbon are not going to participate in hydrogen bonding because carbon is not a highly electronegative element like oxygen is. On this table, we can see a comparison of different alcohols on the top with alkanes in the bottom. If we compare, for example, ethanol, which is CH3CH2OH, with a similar compound, two-carbon compound in the alkanes like ethane, you can see how the boiling point of ethanol is so much more higher than it is for ethane. And that is a very typical pattern. Now, when you increase the nonpolar portion of the alcohol, the boiling point increases even more. That is because the bigger the nonpolar section, the stronger the London dispersion forces that section is capable of. And as you can see here, if we see this sequence of alcohols, each of them representing an increase of one carbon added to the chain as we go from top to bottom, you can see the dramatic increase in the boiling points as you increase the size of the nonpolar portion of the chain. However, as you can see, water solubility decreases with increasing molecular size. That is because the nonpolar portion, as it becomes bigger, makes the molecule more nonpolar and therefore less soluble in water, which is a polar solvent, right? So alcohols with small nonpolar parts, in other words, low molecular weights, are typically water soluble. Alcohols with large nonpolar parts typically are insoluble in water. You can compare here methanol with another one called 1-heptanol. You can see how the molecule on the right has a large organic or nonpolar part, and therefore it behaves more like an alkane than it does like an alcohol. And therefore it makes it less soluble in water. Let's look at some reactions of alcohols. If you remember, we had a reaction of addition where we could add water to an alkene and turn it into an alcohol. The reverse of this would be dehydration. Dehydration typically happens when you have a strong acid catalyst. The OH group of the alcohol is lost from its carbon, and a neighboring hydrogen, in other words, a hydrogen in an adjacent carbon, is also removed, and that converts the alcohol into an alkene and releases water as a consequence. Typically, like I said, the reaction requires concentrated acid and a high temperature in order to occur. Another group of reactions of alcohols involve oxidation. In the oxidation, one way of visualizing is you're going to start with the alcohol, you're going to take out two hydrogen atoms. One of them is going to come from the OH group itself, and the other one is going to come from the carbon where that OH group is attached. The product is going to be water, and the other product is going to be a compound where the carbon has a higher oxidation state. Let's look, for example, at the typical oxidation of an alcohol. Notice that in removing the hydrogen that was attached to the oxygen and the one attached to the carbon, we have generated now a carbon-oxygen double bond. This is a carbonyl compound, and as we saw before, it is a more oxidized carbon than it was in the alcohol. That symbol above the arrow, the bracketed O, represents an oxidizing agent. And oxidizing agents come in different varieties. Some examples are potassium permanganate and potassium dichromate. Now, different kinds of carbonyl compounds will be formed depending on the structure of the starting alcohol and the reaction conditions. For example, let's start with a primary alcohol. The primary alcohol, of course, the OH group is at the very beginning of the carbon-carbon chain. So the carbon where the OH group is attached has two other hydrogens. So oxidation will convert this to a carbonyl group that is terminal. In other words, it's at the end of the chain. Therefore, it will be an aldehyde. Now, most of the time, if the oxidizing agent is in excess, what will happen is the aldehyde will continue to oxidize into a carboxylic acid. So unless we control the level of oxidizing agent or we have a way of stopping the reaction early on, typically the primary alcohol will oxidize all the way to a carboxylic acid. In a secondary alcohol, the OH group is attached to a carbon that has two substituents on it and therefore only one hydrogen. That means that there's only a possibility for one round of oxidation to happen here. The resulting carbonyl compound in this case will be a ketone. Tertiary alcohols do not have any hydrogens attached to the OH-bearing carbon. The carbon in that case is connected to three carbon substituents, and therefore tertiary alcohols will not react with oxidizing agents. Since we mentioned aldehydes and ketones as possible products of oxidation of alcohols, let's go ahead and study the properties of these kinds of compounds. Remember that a carbonyl compound has that C double bond O. Carbonyl groups are strongly polarized with a partially positive charge on the carbon and a partially negative charge on the oxygen. That means that these compounds will experience at least a region of the molecule that will be polar. Remember that in the aldehyde, the carbonyl group is at the very end of the chain, and so the carbon only has one substituent, so to speak, on it. In the ketone, the carbonyl group is inside the chain, so in other words, the carbon is connected to two other carbon-containing substituents. And we draw them many times in this form to emphasize the trigonal planar geometry around that carbon. Aldehydes and ketones typically have distinctive odors. Here we see a perfumer sitting at a mixing table testing combinations of fragrances. Many of these fragrances will turn out to be aldehydes and ketones. Aldehydes are also responsible for some interesting food flavors like vanilla and cinnamon. Let's look at some reactions of carbonyl compounds. First of all, of course, oxidation. Aldehydes, as we saw in the previous section, can be further oxidized by an oxidizing agent to form a carboxylic acid. Ketones, on the other hand, because the carbon is connected to other carbons and to no hydrogens, there is no possibility of further oxidation, and so therefore ketones are not going to respond to an oxidizing agent, whereas aldehydes will. So this is one way you can distinguish between an aldehyde and a ketone. Add an oxidizing agent. If you get a reaction and produce a carboxylic acid, the original compound must have been an aldehyde. If you don't get a reaction, the original compound must have been a ketone. Another possibility, because carbonyl compounds stand kind of in the middle of that sequence of progressive oxidations, is to go backwards and undergo a reduction reaction. When you think of reduction, one way of looking at it is as if you're adding hydrogens across a double bond. So one hydrogen is going to the carbon, the other hydrogen is going to the oxygen. In other words, the product is going to be an alcohol. So if you start with an aldehyde, and again, imagine you bring two H's, one on the carbon and one on the oxygen, you're going to end up with a primary alcohol. If, on the other hand, you started with a ketone, once more, adding an H to the oxygen and another H to the carbon in that carbonyl group will give you a secondary alcohol. So once more, another way of distinguishing between these. Just like with oxidizing agents, there are several types of reducing agents. Some of them are, for example, boron hydride type of compounds, and some other kinds of hydrides are sometimes used as reducing agents. Let's take a look now at the carboxylic acids. This is the other family that we talked about. Of course, carboxylic acids are the ones that have that carboxyl group. Carboxylic acids have relatively high boiling points, and that's due to their ability to form hydrogen bonds with one another. Here are two different molecules of a carboxylic acid, and you can see the formation of hydrogen bonding between the carboxyl groups of each one of the compounds. Looking at this table here, you can see a sequence here of different carboxylic acids where we have essentially added one carbon as we go down the table. And again, you can see the very high boiling points. Not only high boiling points, but also how as you increase the size of the carbon-carbon chain, the boiling point increases, right? Now, the ability to form hydrogen bonds, right, in addition to the polarity of that CO bond, it also gives carboxylic acids significant water solubility. Now you can see that as the number of carbon atoms increases, you have a decrease in the water solubility. Again, the longer the carbon-carbon chain, the more nonpolar the compound is. And even though that increases the intermolecular forces amongst their own molecules, which explains why the boiling point increases, it also makes the molecule too nonpolar for it to dissolve well in water. Of course, carboxylic acids are acids, and so in terms of reactions of chemical properties, we had to consider them as weak acids. And they're about the same as for acetic acid, which is one of the compounds we studied earlier in our discussion of weak acids. So acetic acid, when you dissolve it in water, unlike strong acids like nitric acid or hydrochloric acid, the ionization of this one is reversible. It produces an acetate ion as well as hydronium ions. And remember, we defined the acid ionization constant Ka as the ratio essentially of the ionized over the unionized substances with a value of about 1.8 times 10 to the minus 5. Most carboxylic acids have Kas in that same range as acetic acid. Of course, acids can react with bases. So in this case, we have a substance called benzoic acid, which, as it indicates there, is a solid. And many times the carboxyl group is represented as COOH. And we're trying to kind of like abbreviate it and not write the whole formula. In the presence of NaOH, of course, which is a base, we have a neutralization reaction. The product is water, and a salt, in this case, will be the sodium benzoate. And the ion that is produced when a carboxylic acid ionizes is called the carboxylate ion. And one of the interesting things that happens is that whereas in this case the benzoic acid, the original carboxylic acid, is insoluble in water, the salt produced by it is water soluble. So in general, carboxylate ions are typically more soluble in water than their carboxylic acid conjugates. And that is because you've generated that ionic section there where the carboxyl group used to be, and that allows water to engage in ion dipole interactions. Another interesting reaction of carbonyl compounds and carboxylic acids is a reaction called esterification. Esterification is carried out by warming a mixture of a carboxylic acid and an alcohol in the presence of a strong acid catalyst. So in this case, you can see the carboxylic acid on the left, and you can see the alcohol coming in on the right. Again, remember R prime represent generic carbon-carbon chains. We want to focus on what is happening when these two guys come together. In the presence of an acidic catalyst, what will happen is that the OH of the carboxylic acid and the H of the hydroxyl group of the alcohol will essentially leave as a water molecule and allow then the alcohol and the carboxylic acid to become condensed into what is called an ester. Similar reactions can happen between other carbonyl compounds like aldehydes and ketones and alcohols, but we're not going to be discussing those. We'll limit ourselves to this reaction of esterification. Now, esters have different properties. For example, you can see here where going from left to right, we're going to make from acetic acid, we're going to make an ester called a methyl ester, where the original alcohol was methanol, or an ethyl ester, which was formed with ethanol. Typically, esters are pleasant smelling compounds. Many of the odors of fruits come from esters that are volatile, and therefore they reach your nose and get detected there by your olfactory sensors in there. Simple esters typically have lower boiling points than the acids from which they were derived. You can see here where acetic acid has a boiling point of 118 degrees Celsius, but you can see where methyl ester and ethyl ester have lower boiling points. And that is because as you condense the alcohol with the carboxylic acid, you've essentially lost the ability of these molecules to engage in hydrogen bonding with each other. Now, as you saw in the previous reaction, esterification is a reversible reaction. So the reverse of esterification is called ester hydrolysis. And these can be catalyzed either by acid or by a base. If we have a reaction catalyzed by an acid, as you can see here, the ester on the left is going to be hydrolyzed. In other words, it's going to react with water. Once more, this is the reverse of the previous one. So in this case, the OR portion of the ester and one hydrogen of water are going to recombine to give us the alcohol, and then the carboxylic acid is going to be left behind. In the presence of acid, the carboxylic acid, of course, because of Le Chatelier, remains ionized. Remains unionized. There's another set of compounds that we haven't studied yet, and these are called the amines. Amines are compounds that have one or more organic groups bonded to nitrogen. We could also look at it as if this is a carbon-containing compound that has nitrogen as part of a functional group. If we pretend that we start with ammonia and we start replacing one at a time the hydrogens of ammonia with alkyl groups, we can see that as the process for making and then classifying amines. So if we replace one hydrogen with an alkyl group, we have a primary amine. If we replace two hydrogens of ammonia with alkyl groups, we would have a secondary amine. And if we replace all three of the hydrogens of the ammonia molecule, we would have a tertiary amine. And you can see the structures there in the bottom. Again, the geometry around the nitrogen here will still be sort of like a trigonal pyramid type of structure, just as ammonia does. Now, primary and secondary amines, because they have hydrogens attached to nitrogens, they can form hydrogen bond interactions. Tertiary amines cannot, because there's no hydrogen connected to the nitrogen anymore. And because of that, these hydrogen bonds allow primary and secondary amines to interact via hydrogen bonds and have typically a little higher boiling points. So in terms of physical properties, because of hydrogen bonding, primary and secondary amines have higher boiling points than alkanes of similar sizes. But amines have lower boiling points than alcohols of similar size. Of course, the OH bond is a lot more polar than the NH bond, and so hydrogen bonding in alcohols is going to be stronger than in amines. Here we have a sequence of compounds. On the left, we have butane, in the middle, propylamine, and on the right, propanol. Notice that these three compounds are essentially the same size. They have similar molecular weights. All three of them are extended carbon-carbon chains, but notice how the presence of the amino group, the NH2, increases the boiling point of butane into 48 degrees. But if instead of the amino group or NH2, we put the hydroxyl group or OH, we have now a boiling point that is much, much higher. Stronger hydrogen bonding is possible in alcohols. Again, hydrogen bond interactions can happen with water molecules, either because you have the NH pairs in the amines or because you still have the lone electron pair on the nitrogen atom of a tertiary amine. And so up to about 6 carbons, most amines are very soluble in water. Of course, amines are weak bases. Here we have two of them, methylamine and ethylamine. In the top, we just simply have the ionization of methylamine when you dissolve it in water. Again, notice that it is reversible. It produces what we call a methyl ammonium ion. And of course, just like all bases do in water, you produce hydroxide ions. The equilibrium constant for this, Kb, is 4.4 times 10 to the minus 4. It is slightly bigger than the Kb for ammonia, but most of these amines have Kb's in the same range as ammonia does. Notice in the bottom we have a straight up acid-base reaction, in this case with HCl. And again, the product is a salt of the alkyl ammonium, in this case ethyl ammonium and chloride. These will typically, once you remove the water, will end up becoming solid salts. The other reaction we're going to study is the formation of an amide. This is the reaction between a carboxylic acid and an amine. And as you can see, what is going on here is that as you connect one with the other, the OH of the carboxylic acid is replaced by the nitrogen incoming from the amine. The OH and one of the hydrogens of the amine will get combined to give us a molecule of water. And that is the formation of an amide. And you can recognize an amide because it looks sort of like an ester, except that instead of it being a carbon, oxygen, and then alkyl substituent connection, it's carbon, nitrogen, alkyl substituent interaction. This is a very important process that happens in the synthesis of proteins in our cells. Proteins are made by what are called amino acids, and amino acids have typically one section that has a amino group, one section that has a carboxyl group. Here is the process of making an amide in more detail. Although in the top we have shown the simplified process, the way it happens actually is you initially have an acid-base reaction in which a proton is transferred from the acid to the amine, giving you an substituted ammonium salt, and then you have the carboxylate anion in there. But in the presence of heat, water is removed, and that's how you're getting the amide. The process of making proteins is called a peptide bond formation. A peptide bond is essentially an amide. You have two incoming amino acids. Notice that each amino acid has an amino group and a carboxyl group. The carboxyl group of one reacts with the amino group of the other one to release water and produce an amide. And notice that once you're done that, you still have on one end another carboxyl group that can react with another amino group and therefore generate the long polymers that we call proteins. Well, that has been a very quick survey of all these things, but you should now be ready to do our second assignment, our second organic chemistry dry lab, where you'll do some more nomenclature compounds and then look at some chemical reactions so you can get some practice. Thank you very much. I will see you soon.